Okay, so I want to dig into some examples in the second half of our chapter here. We focus more in on the nuts and bolts of experiments, which are sort of necessarily more complicated than an observational study because the experiment is what is going to be necessary if we wanted to show a causal relationship between two variables. In an observational study, we could obviously observe a correlation, but in order to make sure that there's not another variable that's influencing the response variable, we want to make sure we think of it this way. I want to know that X causes Y. Well, how do I know that this other variable Z is not affecting Y and maybe even affecting X as well? The only way to do that is to set up an experiment where I can control for that third variable, right? Control different settings and situations to see that happen. So one of the things we want to be able to do first and foremost is identify whether something is an experiment or observational study, and we'll have some exercises where we can engage with that. But in this first example, actually this is not my first example. Let me go find it. Yeah, this is the actual first example that I wanted to start with. I got my pages mixed up there. So we have a study. We know this is an experiment, okay? And we want to talk about this one I feel like can be tricky sometimes. The experimental units, so we'll look at that. Our explanatory and response variables, okay? So we'll talk about that. And then the treatments. And this is the big one. If something's an experiment and not just an observational study, then that is our litmus test. We look at it and we can say, these are the treatments. Now, I want to talk about experimental units a little bit here because a lot of times I'll have people read this and we'll look at what's happened here. They want to study two medicines, okay, to treat head lice, right? One medicine is an oral medication, ivermectin, a topical lotion, and a topical lotion containing malathion. Okay, so we've got the ivermectin, which is like a pill, and then this lotion, malathion, both to treat head lice. They studied 812 people in 376 households. Okay, what I'll have people tell me a lot of times is that the experimental units are the 812 people, and that's not true. The way we identify our experimental units is we look and see what's the smallest possible unit that a treatment was applied to. So let's think about how this experiment went down. They're applying the treatments to the 376 households. They're going to the household and we can see it here. Of the 185 households randomly assigned ivermectin, right? We're assigning this treatment to the entire household. So when we go to evaluate the result, we're not counting the people in there. We're counting whether the household was free of lice. Does that make sense? So be careful with that. Sometimes, most of the time, I think it's going to be really easy and obvious, but sometimes I think that can be a little bit tricky. Okay, so what are the experimental units? That's the first question. So in this case, the experimental units would be the 376 households, not the 812 people. Okay, what are our explanatory and response variables? This might be a little bit easier to identify. So the explanatory variables here are our two medications, right? So it's the type of medication. Okay, what medication did they use? Did they get ivermectin, or did they get the topical lotion malathion? Okay, the response variable is just whether or not there is lice presence in the household. So the presence of lice. Okay, it's a yes or no, whether or not there's lice in that household or not. Okay. And then finally, we have the treatments, right? What were the treatments? There were two. Okay, we had the ivermectin and malathion. Those are my two treatments. So one of the things I find is difficult sometimes for students is feeling like you need to be an expert in a field. So, here we are answering a question. This is the nature of statisticians all the time. Oftentimes I'm faced with this. If there's a colleague or if there's a student or friend that's in graduate school and they want to publish research, I have to minimally be able to converse with them about what it is that's happening. So sometimes we have to do the best we can to wrap our head around a situation with a lice medication. And then the next thing we know, we're we don't have to be an expert farmer or gardener, but I need to be able to at least read and dissect what's happening in that situation and not feel pressured to be an absolute expert in some kind of field of science, but just to be able to apply what I know about statistics, and especially in these situations, designing these experiments to control for other factors. So here we have a question that we want to focus in on. Oops, back to my whiteboard. I just wanted my highlighter. This is the research question. Does adding fertilizer affect the productivity of tomato plants? So that's our question. That's what we want to think about the whole way through there. Okay. How about the amount of water given to the plants? So there's two questions they're asking here, right? We have fertilizer and then we also have the water. How do we know which one is affecting which situation, right? So we're going to have to try our best to control for both of those. So the gardener plants 24 similar tomato plants. Okay. So here's something he's controlling for, right? The plants are at least similar in identical pots in his greenhouse. So again, he's controlling for the type of pots he's using. He's controlling for really like sunlight and probably a lot of other variables by having the greenhouse, right? So here we have all these controls that we can observe in this experiment. He's going to add fertilizer to the soil in half of the plots, okay? So what we're going to have right away is we're going to have one group that gets fertilizer and the other group gets no fertilizer, okay? Now, also, he's going to give water 8 of the plants with half a gallon of water per day, 8 of the plants with 1 gallon of water per day, and the remaining 8 plants with 1.5 gallons of water per day. So every single tomato plant is going to get water to some degree, but only half of them are going to get fertilizer. Okay, so hopefully we're tracking with that, and we want to answer a couple of questions here now. All right. At the end of the 3 months, he's going to look at the total weight of tomatoes produced on each plant. So we'll take the plants, and I would imagine he's going to look at the treatments that they received and see, and then compare the results that way to see, which one of these variables do we think affected the most. Now, there's, for me, thinking about the fact that every plant's getting some amount of water could be an issue, right? He's trying to ask if fertilizer or water, which one of those is more effective, but he has no group that gets no water. He does have plants that get no fertilizer, so it's worth thinking about in terms of setting up this experiment to answer those two research questions. So, identify the experimental units or subjects. So again, remember, what is the smallest unit that we are applying a treatment to? Okay, so hopefully we said the experimental units or subjects are the individual tomato plants, right? Each one of those plants is going to receive a treatment, okay? Looks like we have 24 of them, right? What are the explanatory and response variables? So the explanatory variables, we're going to have 2, right? We have presence of fertilizer, whether fertilizer was admitted or not. Okay, that would be one, whether or not they received fertilizer. And then the other would be amount of water, because there's no saying water or not water, right? So fertilizer is, yes or no, did it receive fertilizer or not? And then we're going to look at the amount of water. So those are our 2 explanatory variables. And then the response variable is going to be the weight of each plant. All right, it says after 3 months, so it's the same amount of time that all these plants are receiving treatment. Again, another control there that will look at that response variable. Okay, so to think about here, one of the struggles that oftentimes this particular chapter, it seems, there's like only 2 sections. There's not a lot of computation, but it really is a challenge sometimes for students. And something like this is why I think a lot of times we don't sign up for a math class, because we like to read a paragraph, and we really have to read, and we have to read really, really carefully when we go through these situations. So, researchers in Canada performed an experiment with university students to examine the effects of in-class laptop use on student learning. So again, I like to think about, they want to know what are the effects of in-class laptop use on student learning. So all participants in the study were asked to attend a university-style lecture and take notes with their laptops. Now, half of the participants were assigned to complete other non-lecture related online tasks during the lecture. These tasks were meant to imitate typical student web browsing during classes. The remaining students simply took notes with their laptops. So we have one group that's kind of multitasking, the other group that's just taking notes on their laptops. To assign the treatments, the researchers printed 40 papers with instructions, 20 with multitasking, 20 without, shuffled them and handed them out. So that's important. We don't want to give people an option of, which one of these things they would like to do. We randomly assign the treatments. We always want that to be part of our experimental design. And at the end of the lecture, all participants took a comprehension test to measure how much they learned from it. The results, students who were assigned to multitask did significantly worse, 11%, than students who were not assigned to multitask. Okay, so if you're asking what are these 4 principles of experimental design, then make sure you're also reading our PowerPoint slides, right, that are found in our Schoology. The principles of experimental design are right there. This looks like the 8th slide there. We have a comparison, right? We want to have a design that compares 2 or more treatments. And one of the treatments could be a no treatment. That is what we call a control group. Random assignment so in other words, like if all the students in the class just used a laptop and took notes, we wouldn't really be able to see the effects of the outcome. So use chance to assign experimental units, random assignment. So I don't have a clever acronym for this. We have CR, if that's helpful to remember. Control, if there's any other variables that might be affecting things, we want to control for that. And then replication, do we have enough experimental units? Or also replication could mean that we've actually done the replication more than once. So do we see these 4 elements in the experiment? For sure. We do see comparison, right? They compare this half of the participants that are assigned to complete other non-lecture tasks, and then they also compared and they looked at their scores at the end. One group was 11% better than the other. So there's our comparison, right? So we definitely have the comparison element here. Then we look at randomization, right? Did he randomize? Yep. To assign the treatments, 40 papers with instructions, 20 multitask, 20 without. He shuffled them and handed them out. Okay, CR. And then the second C was control, right? Did they control for other variables that could influence the outcome in this situation? Okay, so one of the factors here, it says at the end of the lecture, they all listened to the same lecture, right? They all took the same comprehension test. So we measured those things the same way, and it looks like they're all university students, right, at the same university. It wasn't in different places. So all of those are things that could affect the outcome if you had different professors giving the lecture. Then we wouldn't really be controlling for that. So they all listened to the same lecture. So what we're really trying to do again is look at what was the only thing that could have affected the test results. The directions they received on the slip of paper. We want to control for everything else that could possibly influence those results, so that the only thing that's affecting the outcome would be the instructions that they got. And then finally, replication. We had 40 participants, right? We didn't just do this with 2 people or 40 participants. There's your replication. Okay, so if we look at this, I'm going to jump right to where it says problem. Describe a completely randomized design for this experiment, right? A few sentences describing how you would implement your design. So let me talk about 2 things I want you to do if you're asked to design an experiment that will help you. Number 1, I want you to kind of draw it out or diagram it out. If you don't know what I mean, you can look back at some of the PowerPoint slides. But then also write a couple of sentences. What I want you to think about when you do this is, if you wanted somebody to implement this experiment, to do it, would they be able to read your directions and then execute it? Okay, so let's see what they want to do here. The psychologists want to know how different types of television shows impact young children. Okay, there's their research question. So they have 64-year-olds, that's their replication, and have them watch 9 minutes of fast-paced. Okay, so my 11-year-old just shattered a glass. You probably heard it. Everything's good now. So we have 64-year-olds. They're going to do 9 minutes of a fast-paced children's program, 9 minutes of a slow-paced, and draw for 9 minutes. And then after 9 minutes, they'll complete several tasks. That's going to be our metric to see, how these different treatments impact their mental capacity, right? So they want to see if there's any impact at all, depending on how these three different treatments go. So what I'll do first is sort of draw this out, and I'll show you what I mean with an outline. So I'm going to, somebody can look at this and they'll have it outlined, but then I'm going to write a couple sentences below so that they clearly could implement it. So I'm going to have my 60 4-year-olds. Okay, and what I want to happen with these 60 4-year-olds is I want them to be randomly assigned to one of three groups. So this is I'm gonna write random assignment here, and then I'll explain or unpack how I'll do that. Okay, so I'll call the groups treatment A. This is fast-paced. And you don't have to call them treatment A, treatment B. I'm just doing it. I mean, if you just call it fast-paced, that's fine. And then we have slow-paced. And then we have draw, right? We can call that group C if we want. Okay, and then what are we going to do? We're going to do our tasks and tests. And they all take the same tasks and tests. Okay, and then what we'll do finally is compare the results. Now, this is what we've already done this year, right? Maybe we take the average test score, or somehow we have a way of measuring the tasks. Were they able to complete it or not completed? So at this point in the course, we found many different ways that we can look at metrics to compare those results. So I provide an outline, and then the next thing I want to do here is, write a narrative, provide a narrative that, describes to somebody how they would go ahead and implement this. Okay, so I'm going to write a few sentences here. I'm going to take 60 slips of paper. On 20 and draw on 20. Okay, have each 4-year-old select a paper at random from a bowl. Some people say they put it all in a hat. You might need a pretty big hat for that. See if I can move this text box. Yeah, I like my text box there a little bit better. See if I can continue typing in there. So have each 4-year-old select a paper at random from a bowl. Students will be grouped, or children, according to the treatment they received. Have all students engage in the treatments, which they've already described. We don't need to re-describe them. And then we want to have all students, or 4-year-olds, complete the same tasks and tests under the same conditions. That's what we control, right? If possible, we can have the same person read the direction to them, tell them what they want to do. Okay, and then we, maybe measure the average test result for each group. And compare the scores. Okay, seems like a lot, but I would feel comfortable if I gave this to someone and said, can you implement this experimental design? that they would be able to do that. So notice I've written a few sentences. Sometimes what I find is that folks will write a few sentences and then I still feel like there's some information missing. And if they draw the diagram to go along with it, it seems like we're able to cover all of our bases. Okay, so this next situation here is going to involve what we call a block design, which is going to feel really similar to stratified random sampling in our observational studies. So let's jump into it. We have a popcorn lover wants to know if it's better to use the popcorn button on the microwave or use the amount of time recommended on the bag of popcorn to measure how well each method works. She will count the number of unpopped kernels remaining after popping to obtain the experimental units. She goes to the store and buys 10 bags of each of 4 different varieties of popcorn: butter, cheese, natural, and kettle, for a total of 40 bags. Okay, so, well, on a sidebar here, I've found that if you kind of got to hang around the microwave and listen. Once you hear the kernels, once you hear like 3 seconds in between pops, you better take it out. It's probably getting burnt. That's my personal opinion. But popcorn button could be convenient if you don't have the time to sit there and listen. So randomized block design means that we believe there's a variable that can affect the outcome, right? And I guess the way we would measure, she's going to measure the unpopped kernels, which is a good metric. So we're going to look and see how many unpopped kernels there are, and it's really, really possible that if you do the exact same thing to butter popcorn and the same thing to kettle corn, then maybe the butter popcorn has fewer unpopped kernels just because it's butter. The type of popcorn that we're using could very easily affect the outcome. So if we just randomly assigned 20 bags and did not pay attention to the type of popcorn we were popping, 20 bags to get the popcorn button and then another 20 to get the timer, then those results would be muddied in there. We call that a confounding variable or a lurking variable. It would make it really hard sometimes to see the results. In using a block design where we separate, we can look at the results within each block. And the big reason for a randomized block design, always, if you want to try to remember this, is to reduce variation. You're going to have a lot more variability in the results, and we usually do a demonstration of this in class. I'll try to make a video of it and explain it to you, where we set up like a matched pairs design, and it's a simulation, and we work through it. We just can't do that under the current circumstances, but it's a good way to observe how to implement a block design and also the advantage of it. But the main purpose is to reduce variation. Think about a metric like standard deviation. If we found the average number of kernels per bag and we never separated by butter, cheese, natural, and kettle, we would have a much higher standard deviation in that bigger group than if we broke them up into smaller groups first. So when you have less variation, a lot of times it allows you to make better conclusions, to see the results more clearly and control for those outside variables. Okay, so that's how I would explain why we would use a block design in part A, right? Explain why a randomized block design might be preferable, right? Because type of popcorn could easily influence the amount of unpopped kernels. So if we control for that, if we break it down and look at just butter and look at what happened with the popcorn button compared to the timer inside a butter block and then inside a cheese block and natural and kettle and so on. So in outlining this and describe how we would carry this out, that's the same thing we just did in our previous example. So the first thing I'm going to do is create an outline of this, and the very first thing that would happen is we would have our 4 blocks. So my blocks would be butter. We established that first. Notice I'm not doing this is not at random. I'll have students sometimes say, create your blocks at random, and that right away tells me they don't really understand the block design at all. So I have my 4 blocks, okay? And then what's going to happen in each one of these blocks is what we just did. This is going to be random assignment. Okay, and what are the 2 groups? What are the 2 treatments? We get the popcorn button, or we use the time method. Popcorn button, right, versus time, right, as described. Popcorn button and time method, and so on. Okay, now what happens? We measure unpopped kernels. Okay. Measure or count. Okay, and then maybe we compare the averages. Right, we have 5 bags each. We could just average them and compare them, or we could just do total. Doesn't matter, but we want to have some kind of comparison. That's probably something that you could write up in your narrative as you're explaining it. So this is what the outline would look like, right? You show that you have your blocks created, and then you have randomization. So we do the same thing, but we do it 4 times. So right here kind of just looks like what I just did in the previous example, but I have 4 of them, 1 for each block. Okay. Okay, so type of popcorn will be each block. Randomly assign 5 bags of each type to each treatment. And how can I randomly do that? Well, I can just shuffle them up, right? I could have all the bags in a bowl, shuffle them up, grab one that reach in, grab it, it goes into one treatment, reach in, grab the next one, goes into the other treatment. That would be a perfectly fine way to establish the randomization. Or we could again put in slips of paper. You could have 2 bags, you could toss a coin, and if it's you don't want to just toss a coin for each bag. That could be confusing, because what could happen then is you could get 7 heads, and if 7, that means they're all popcorn, but we want 5 of each. So whatever you do there, make sure that there's 5 of each, right? So you could have 10 slips of paper in that situation. Five popcorn button, and then 5 timer. Okay. After all of the popping, okay, so my screen got a little busier than I wanted to be there, but type of popcorn will be each block. Randomly assign 5 bags of each type to each treatment. I'd like to explain how I'm going to do that. So I've like I said, I could just have all 10 bags. I reach in, grab one. That one's going to get a timer. Reach in, grab the next one. That one's going to get the popcorn button. Do it again, right? Every, reach in. Next one I grab. So I'm reaching into the bowl blindly. I could be literally grabbing these bags of popcorn out of a giant bowl and assigning them to the treatments. Or 10 slips of paper, however you want to explain that is fine. So we want to explain clearly that we're going to do a comparison within each block, but then we could also follow that up and compare. Looks like overall butter had less unpopped kernels than cheese anyway. We could do those comparisons as well. It opens us up to see, in general, on average, regardless of the method, kettle corn had the least amount of unpopped kernels. Certain conclusions like that could be made. But that's the essence of the block design, and the purpose of it is to reduce variation from a variable that we know could affect our response variable.